Hi everyone, this is Santhi from Department of Mathematics and Statistics from Bhavan Vivekananda College of Science, Humanities and Commerce. So I am here with my lesson 6 from Linear Algebra on vector spaces. In this lesson, I am going to explain few more examples on vector spaces and properties of vector spaces. Let us see the first example. Let W be the union of first and third quadrants in the xy plane. That is, W is the set of all column vectors xy with two rows such that product x into y is greater than or equal to 0. Then A bit is, if U belong to W, if there is any vector U in W and C is any scalar, then the product CU is it in W? That is the question here, and give reasons for this. And B bit is, find two specific vectors U and V in W such that the sum U plus V is not in W. So we are going to solve this problem. First one, what is W for us here? It is the set of all the vectors xy, column vectors, such that product xy is greater than or equal to 0. And it is given that W is the union of first and third quadrants in the xy plane. So let us take xy plane. So what is the first quadrant? What will be vectors in the first quadrant? So here I am just shading the first quadrant, and then the third quadrant is this one, where you have in the first quadrant we all know that both x and y are positive, and in the third quadrant we know that both x and y are negative. And here even you have x-axis, positive x-axis, and then negative x-axis, positive y-axis and negative y-axis also. All these are the possibilities for x and y to be. So now let us see how do we go through this problem. U is equal to set a vector xy such that product xy is greater than or equal to 0. The product xy is greater than or equal to 0 implies we have different cases. Case 1, x, case 1 is x is equal to 0. So when x is equal to 0, then product xy greater than or equal to 0. Case 2, y is equal to 0. And case 3 is x is 0 as well as y is also equal to 0. Case 4 is x is greater than 0, y is greater than 0. And then case 5 is x is less than 0, y is less than 0. In all these 5 cases, then the product xy will be either greater than 0 or it is equal to 0. So the product xy will be satisfying the given condition in all these 5 cases. X is 0 first case, second case is y is 0, third case both x and y both are zeros, then the fourth case x greater than 0 and y greater than 0, and the last case x less than 0, y less than 0, then also the product xy will be greater than or equal to 0. Now we will check the first one using all these cases, possible cases. We'll check the first one, a bit, in the given question whether it can be true or not. So for this, what do we do is we will consider a scalar. So because C we need it, so let C be a scalar, any scalar, right? Let C be any scalar. Then case 1. What is case 1? Case 1 is x is equal to 0. Then what will be C into U? C into U is equal to C into xy, which is equal to C into 0y, that is equal to 0 cy. Then what is the product of 0 and cy? 0 and cy product will be 0. So in this case, what is happening? The product xy will be greater than or equal to 0. So either it is greater than 0 or equal to 0, condition is satisfied. So in this case, we can say Cu is belong to the vector Cu belong to W. So the condition is satisfied in case 1. What about case 2? case 2 y is equal to 0. So in this also c into xy is equal to c into x0, which is equal to cx0. That is cx into 0 is equal to now is also equal to 0. So in this case also product xy greater than or equal to 0. And then we have in this case also the product CU, scalar multiplication CU, belong to W. Now next we will see what is case 3. Case 3 is both x is equal to 0, y is equal to 0. Then in this case c into xy is equal to c into 0, 0, which is equal to 0, 0. Then here you have, so here instead this I got it, so c into 0, 0 is equal to 0, 0. Therefore we have the product xy, that is 0 into 0, is equal to 0, that is either greater than or equal to 0. Therefore in this case also I have cu belong to W. Case 3 is over. Next we have to go for the next case, case 4. What do we have in case 4? Case 4 we have x greater than 0, y greater than 0. Both x and y are positive. Then c into xy is equal to c into vector xy, which is equal to cx into cx cy. Then what is the product of these two components? Cx into cy is equal to c square into xy, which should always be greater than or equal to 0, because we know xy is greater than or equal to 0. C square will be greater than 0, xy greater than or equal to 0. Therefore, you have here the product of these two components greater than 0. Therefore, Cu belong to W in case 4 also. Now let us go for the next case. Case 5. So what is case 5? X less than 0, y less than 0. Then c into xy is equal to cx cy. Then cx into cy, the product of these two components. Here also it is c square into xy. This will be also greater than or equal to 0. For the same reason as explained in the case 4, c square greater than 0 and product xy is greater than or equal to 0. Therefore, c square into xy greater than or equal to 0. Hence, in this case also, the product Cu belong to W. So, by this, in all the possible 5 cases for the vectors which are in W, we have by all the above 5 cases, we have Cu belong to W. So, we have completed the first one for all u belong to W and for any scalar C. Now, so we have the second one, B bit. What is that B bit? Find two specific vectors u and v in W such that u plus v, the summation u and v, is not in W. So I have to give some specific examples. So I am taking here randomly, I am picking two vectors. U is equal to, which is xy, and where the product xy greater than or equal to 0. And let me take u is equal to 3, 5, and then v is equal to -2, -8. Then where this u comma v belong to W, because they satisfy condition u plus v is equal to 3 minus 2, 5 minus 8, which is equal to 1 minus 3. But what is, can this u plus v be in this? But here you have 1 into minus 3, that is x into y, 1 into minus 3 is equal to minus 3, which is less than 0. So in this case, what is happening here, u plus v cannot be in w, does not belong to w. This is what the example that we gave here, for that summation of these two vectors u and v cannot be in w. So apart from this, whatever the points asked in the example, can we say now that this set of vectors W form a vector space? No. Why? Because here you have the vector addition u plus v is not again a binary operation in W. Though the scalar multiplication is giving again a scalar. So what is that note we have here? W cannot form a vector space with the given operations. It's not asked in the question, but just we are checking like under what conditions a given set cannot be a vector space. Now let us see the next example, example 2. That is, show that the set of all points in R2 of the form 3s, 2 plus 5s is not a vector space. Solution. So what is here h given to us? H is equal to set containing all those vectors 3s, 2 plus 5s. So these are given in coordinate form, not like column vector form, but still they are the same. If you write in column vector 3s, 2 plus 5s you will write. Instead that we are writing it as an ordered pair. So such that S belong to R, any real number. Now we have to check whether it forms a vector space or not. So this we have to do by definition. If we recollect definition, in short, we can remember u plus v belong to w. These are the conditions we'll be having in the definition. Next one, u plus v plus w is equal to u plus v plus w. And then there should be a zero vector and there should be a negative vector for each vector. And then addition is commutative. Next, scalar multiplication, Cu belong to W, and then these two operations, addition and multiplication, should satisfy distributive properties like C into U plus V is equal to Cu plus Cv, C plus D into U is equal to these ones. And next you have the product C into Du is equal to Cd into U, and next you have the last one, that is 1 into u is equal to u, where you have for all u belong to w and 1 is the unity as a scalar. Now let us see the first one. U is equal to 3s, 2 plus 5s. This is the element. So I am taking v is equal to another element 3s, 2 plus 5s 2. Then first condition u plus v is equal to. So how do you add these two? Component wise, 3 into s1 plus s2, so adding these two, it will be giving you 2 plus 2, 4 plus 5 into s1 plus s2. Now the task is whether u plus v be there in H or not. What should be the format for any element to be in H? First coordinate is 3s and the second one is, it should be 2 plus 5 times s. But what did we have? First one we have 3 into s1 plus s2, product of 3. But the second one, if you see, you have here 4 plus 5 s1 s2, which does not belong to H. Why? Because the second component should be in the form of 4 plus 5 s1 plus s2, it is there, but it is not equal to 2 plus some 5 into some scalar value. That means the summation u plus v cannot be in H, therefore H cannot form a vector space. We have now properties of vector spaces. Under these properties of vector spaces, we have a small theorem, that is, for each vector u in V and scalar C, we have number 1, 0 into u is equal to 0. Number 2, C into 0 is equal to 0. And number 3, minus u is equal to minus 1 into u. So if you observe in the first one, left hand side I have written 0 small 1 and the right hand side I have written little bit bigger 0. What does it mean? The left hand side 0 is a scalar, that is numerical 0, which is multiplied with vector u, that gives you 0 vector. So right hand side I have written a little bit bigger 0, which represents 0 vector. Right, that means it can be like a column vector which has all zeros in that particular vector space, or it can be a zero polynomial, or it can be a matrix with all the 0 elements, that is, which is on par with 0 in that particular vector space. In the second one I wrote there, C into 0 is equal to 0. Both left and right hand side you have 0 is the same, that is 0 vector. C scalar is multiplied by 0 vector, so that the result is equal to 0 vector. In general, these properties are which are very normal, we see even with the numericals, that is with scalars. Now we'll prove these for the vectors also. So let us look at the proof now. So when we start the proof, so you are given here with a vector space V, and then you have a scalar C. So, and there is a vector u in V. So the first one I have taken, we have to prove 0 into u is equal to 0. So I'll write first 0 into u as 0 plus 0 into u. So what did I do here? The left hand side 0, I wrote it as 0 plus 0, because 0 scalar can be written as 0 plus 0, which implies 0 into u is equal to right hand side, apply the distributive property which is among the definition. 0 into u plus 0 into u, that is from the definition of the vector space. What did you have there in the definition? C plus D into U is equal to C into U plus D into U. Then which implies, now I have here on the left hand side 0 into U. For that, this is a vector 0 into U. So I can add a 0 vector to that. So I wrote 0 U plus 0 is equal to 0 into u plus 0 into u, because what did I do on the left hand side? Just to the vector 0 u, 0 into u, I added a 0 vector. So in any vector space, what is the property of 0 vector? You add that vector u plus 0 is equal to u. Therefore, I can write here for 0 into u in the second step, I can add 0 vector. Its value does not change. Then which implies, if you apply the left cancellation law, so left side 0 into u here, and on the right hand side 0 into u on the left, then you will remain with 0 is equal to 0 into u. That is what you have to prove in the first one. So this is by left cancellation law. So first one we have proved it. Now we'll go for the second one. In the second one we have c into 0 is equal to 0, we have to prove. So I'll take c into 0. So c into 0, again I'll write this as c into 0 vector plus 0 vector. In the previous you have written 0 scalar plus 0 scalar. Now you are writing 0 vector as sum of two 0 vectors, which will be true in a vector space. So which implies I have here left hand side it is the same c into 0. 0 vector is equal to, apply distributive property, c into 0 plus c into 0. This is that property, that condition in the definition of the vector space, that c into u plus v is equal to c into u plus c into v. So if you apply that, you can write c into 0 plus 0 is equal to c into 0 plus c into 0. Now again to the left hand side, c into 0, add again 0 vector, same as in the previous one. For 0 into u, you added 0. So you get c into 0 plus c into 0. Then again, left cancellation law, apply left cancellation law. So c into 0 will be cancelled, and you will have 0 is equal to c into 0 by left cancellation law. So let us mention the same thing even above in the first one, where we used there that left cancellation law. So that is also by left cancellation law, which is true in all the additive groups. And we know that vector space first it is additive group. So you have proved now 0 is equal to c into 0, the second one. Now we'll prove the third point, that is to prove that minus u is equal to minus 1 into u. So to prove this one, we will use the first condition what we proved in this same theorem. What did we prove in the first one? That is, we have 0 into vector u is equal to 0 vector. That is from 1. In 1 we proved 0 scalar into u is equal to 0 vector. Now left hand side 0, I'll write it as minus 1 plus 1 into u is equal to vector 0. Why? We know that in scalars minus 1 plus 1 is equal to 0. In real numbers, that is scalars, or you can say in any field, that field is denoted by f. So I'll write r or f. Now left hand side, apply distributive property, minus 1 into u plus 1 into u is equal to 0. Why? Because I have c plus d into u is equal to c into u plus d into u. So if I apply this, I can write this. And now here, sum of two quantities on the left hand side, these two are zeros. So we can recollect something, that usually in when you learn group theory, you have, if a plus b is equal to 0, then a is equal to minus b, or you will write it as b is equal to minus a. That means a and b are additive inverses of each other. If sum of two elements is 0, then each one is the additive inverse of the other element. Now if you see here, left hand side, what we have minus 1 into u plus 1 into u. We can write it as u is equal to 0. Sum of two elements is 0, implies minus 1 into u and u are additive inverses of each other. This is what we just mentioned here. A plus b 0 means a and b are additive inverses of each other. Therefore, you can say minus 1 into u is equal to, so what is additive inverse of u? Minus u. So minus 1 into u is equal to minus u. So this is what we have to prove in this theorem, the third point.